Welcome to this gentle exploration of the universe's most extraordinary moment, a time so brief, so violent, so impossibly strange that our everyday minds can scarcely hold it. Tonight, we drift into the story of cosmic inflation when everything that would ever exist, every galaxy, every star, every atom in your body, underwent the most dramatic transformation imaginable in a period far shorter than the blink of an eye. Close your eyes for a moment and try to imagine a fraction of time so small that even light, racing at its cosmic speed limit, could barely move the width of a proton. We're speaking of 10 to 36 seconds, a decimal point followed by 35 zeros, and then a 1. It is a duration that exists more in mathematics than in human experience. A whisper of time that passes before time itself has truly begun. And yet, in this infinitesimal instant, the universe accomplished something that defies our deepest intuitions about how reality should behave. Picture, if you will, the universe at this primordial moment. It was smaller than an atom, smaller than a proton, smaller than anything we have words to properly describe. The entire observable universe, all 93 billion light years of it that we can see today, was compressed into a region so tiny that it makes a grain of sand seem like a vast cosmic ocean. Within this incomprehensibly small space, there was no matter as we know it, no atoms, no particles, not even the fundamental building blocks that would later dance together to create everything. There was only energy in its purest form, and space itself, pregnant with possibility. What happened next was not an explosion in the traditional sense. The Big Bang, despite its name, was not like a firework bursting outward into empty space. There was no empty space for it to burst into. Instead, space itself began to expand, and not gradually, not gently, but with a ferocity that beggars belief. In that first fraction of a second, the universe didn't just grow. It underwent what physicists call inflation, a period of exponential expansion where the fabric of space-time stretched faster than light could cross it. There is something almost musical about this moment, a cosmic crescendo that played out on scales both impossibly small and unimaginably vast. Every point in that tiny universe was simultaneously the center, and every direction was both inward and outward at once. The distinction between here and there had not yet solidified. Causality itself, the simple notion that cause must precede effect, was still finding its footing in a reality that was inventing its own rules, moment by moment. The strangeness multiplies when we truly contemplate what it means for the universe to have been so small. Within that infinitesimal volume existed the potential for everything: the Andromeda Galaxy and the Milky Way, the light from distant quasars, the iron in Earth's core, the calcium in your bones, the very neurons firing in your brain as you listen to these words. All of it compressed into a space far smaller than the period at the end of this sentence. It challenges not just our physics, but our philosophy, our ability to make sense of existence itself. And here's perhaps the most beautiful paradox. This moment we're describing, this explosive instant of creation, is simultaneously the most violent and the most peaceful event in cosmic history. Violent because of the sheer energy density, the raw power of space-time undergoing exponential expansion. Peaceful because there was nothing yet to be destroyed, no structures to tear apart, no complexity to unravel. It was pure becoming, existence rushing forward from potentiality into actuality, a universe learning how to be a universe. The ancient philosophers wondered whether the world had a beginning or whether it had always existed. They could never have imagined that the answer would be stranger than either option, that the universe did have a beginning, but that beginning was so bizarre, so far removed from ordinary experience, that it would take humanity thousands of years of careful observation and mathematical insight to even begin to glimpse its nature. As we drift deeper into this mystery, we must hold in our minds a curious duality. On one hand, we're describing events that happened 13.8 billion years ago, in the first fleeting instant after time itself began. On the other hand, we're describing something that is, in a very real sense, still happening. The light from the cosmic microwave background, the faint afterglow of the Big Bang, is reaching us right now, carrying with it whispers of that inflationary epoch. The expansion of space continues, though at a far more leisurely pace. The universe is still unfolding, still becoming, still writing its story across the canvas of space-time. Yet this is only the beginning of the story. Before we can truly understand what inflation accomplished, we must first understand the puzzles that demanded such a dramatic solution. For you see, cosmologists in the mid-20th century found themselves confronting a universe that shouldn't exist, at least not in the form we observe. The universe appeared to have been fine-tuned, adjusted with almost impossible precision, and this troubled them deeply, not because they believed in divine intervention, but because physics should explain what we see without requiring billions of cosmic coincidences. And so we turn our attention to the mysteries that inflation was born to solve, to the questions that kept cosmologists awake at night, staring at the ceiling and wondering how the universe could possibly be the way it is. In the quiet depths of theoretical cosmology in the 1970s, a profound unease was growing. The universe that scientists observed, ordered, uniform, geometrically flat, seemed to require a series of initial conditions so precisely arranged that it felt less like physics and more like cosmic sleight of hand. Three problems in particular haunted the minds of cosmologists. Three puzzles that suggested something fundamental was missing from our understanding of the universe's birth. The first was called the horizon problem, and it remains one of the most elegant mysteries in all of cosmology. When we look out into the universe in opposite directions, we see regions of space separated by distances so vast that light hasn't had time to travel between them in the entire history of the cosmos. These regions are, in the language of physics, causally disconnected. They have never been in contact with each other, never exchanged information, never influenced one another in any way. And yet, when we measure the temperature of the cosmic microwave background radiation coming from these opposite ends of the sky, we find that they are the same to within 1 part in 100,000. Imagine two orchestras on opposite sides of the earth, never having communicated, never having heard each other play, and yet performing the same symphony in perfect synchronization, hitting the same notes at the same moments with the same dynamics. You would immediately recognize that something had coordinated them, that there must have been some prior connection, some shared rehearsal. The universe presents us with exactly this situation But on a cosmic scale, how did regions that could never have communicated manage to reach the same temperature, the same density, the same properties? The standard Big Bang model offered no answer. It simply required us to accept that the universe began in an extraordinarily uniform state, that by cosmic coincidence, every region just happened to start with precisely the same conditions. For a discipline built on explaining the present through the past, this was deeply unsatisfying. It felt like cheating, like pushing the mystery back one step and declaring victory. The second problem was equally troubling, though more subtle. It concerned the geometry of the universe itself, the curvature of space-time on the largest scales. Einstein's general relativity tells us that the universe can have one of three geometries. It can be positively curved like the surface of a sphere, negatively curved like a saddle, or perfectly flat like an infinite plane. The geometry depends on the density of matter and energy in the universe. If the density is exactly equal to a critical value, not a tiny bit more, not a tiny bit less, then the universe will be flat. When cosmologists measured the density of the universe, they found something remarkable and disturbing. The universe appeared to be flat, or very nearly so. But here's the problem. Flatness is not a stable state in the standard Big Bang cosmology. A universe that starts out even slightly curved will become more curved over time, just as a small deviation from vertical will send a pencil balanced on its point tumbling to the table. For the universe to be as flat as we observe it today, it would have needed to be flat to within 1 part in 1060 in the first second of its existence. There is something profoundly calming about contemplating such a number, even as it troubles the mind. 1 part in 1060, a precision so extreme that it makes the finest Swiss watchmaker seem clumsy by comparison. If the universe's initial density had been off by the tiniest fraction, by an amount so small that we lack even metaphors to capture it, we would live in a cosmos either collapsing back on itself within moments or expanding so rapidly that no structures could ever form, no galaxies, no stars, no planets, no life. And yet, here we are, existing in a universe balanced on this knife's edge. Why? The third problem was more technical, but equally vexing. It concerned magnetic monopoles, hypothetical particles that would be the magnetic equivalent of an electric charge. Many theories of particle physics in the early universe predicted that monopoles should have been produced in enormous quantities during the first moments after the Big Bang. In fact, there should be so many monopoles that they would dominate the mass of the universe, making it impossible for matter as we know it to exist. But when physicists searched for monopoles, they found nothing. Not a single one has ever been conclusively detected. The universe appeared to have started with the conditions necessary to produce monopoles, but then somehow avoided producing them, or produced them and then made them vanish. It was like finding a factory with all the machinery to manufacture cars, but discovering that no cars had ever been built. These three problems, the horizon problem, the flatness problem, and the monopole problem, formed a trinity of cosmic mysteries that seemed to require either an extraordinary series of coincidences or a fundamental revision of our understanding of the universe's first moments. Some physicists spoke of fine-tuning, suggesting that the initial conditions of the universe had been adjusted with exquisite precision. But this raised more questions than it answered. Adjusted by what? by whom, and why these particular values. There is a certain humility that comes from facing such mysteries, a recognition that the universe does not owe us simple explanations. The cosmos is not obligated to make sense to creatures who evolved to understand the flight of thrown rocks and the ripening of fruit. And yet, the scientific impulse, the drive to find patterns and principles, refused to accept coincidence as a final answer. Late at night in universities around the world, cosmologists stared at their equations and wondered. The mathematics was clear. The standard Big Bang model worked beautifully to describe the universe from a fraction of a second after its birth all the way to the present. But those initial conditions, that first moment, remained shrouded in mystery. It was as if someone had set the cosmic stage with impossible precision and then walked away, leaving only the performance for us to observe. Meanwhile, across the vast expanse of theoretical physics, ideas were brewing that would transform this picture entirely. The solution, when it came, would be both elegant and radical. It would suggest that the universe had undergone a period of transformation so dramatic, so far removed from everyday experience, that even calling it an expansion seems inadequate. But before we can understand the solution, we must first grasp something even stranger: the nature of space itself and what it means for space to grow. There is something almost musical about the way we casually speak of the universe expanding, as if we all understand perfectly well what this means. But buried within this innocent phrase lies one of the most counterintuitive concepts in all of physics, a notion so strange that even Albert Einstein initially resisted it. Tonight, let us drift into the peculiar nature of cosmic expansion and discover why the phrase faster than light does not mean what you might think it means. When you think of something moving faster than light, perhaps you imagine a spaceship accelerating through the cosmos, racing past stars and galaxies in violation of Einstein's cosmic speed limit. But cosmic inflation, and indeed the expansion of the universe generally, is nothing like this. Nothing is moving through space. Instead, space itself is growing, stretching, increasing in extent between every point. It's not that galaxies are flying away from each other through space, but rather that the space between them is expanding, carrying them along like raisins in rising bread dough. This distinction, though it sounds subtle, changes everything. Einstein's special relativity tells us that nothing can travel through space faster than light. This is not merely a practical limitation, like a speed limit on a highway. It's woven into the very fabric of cause and effect, into the structure of space-time itself. If you could send information faster than light, you could, in principle, send messages backward in time, creating paradoxes that would unravel the logical consistency of the universe. The cosmic speed limit is there for a reason. It preserves causality, the orderly progression of cause and effect that makes physical law possible. But, and here's the beautiful loophole, Einstein's general relativity, which describes gravity and the geometry of space-time, places no limits on how fast space itself can expand. Space is not a thing that moves through something else. It is the stage on which all motion occurs. When space expands, it doesn't violate relativity because nothing is actually moving through space faster than light. The galaxies themselves maintain their local speed limits. It's the distance between them that grows. Picture, if you will, an ant walking across a rubber sheet. The ant has a maximum speed it can walk, say 1 centimeter per second. Now imagine that the rubber sheet itself begins to stretch. The ant continues walking at its maximum speed, never exceeding its personal speed limit. But the distance between where it started and where it's going increases faster than the ant can cover it. The ant isn't breaking any rules, isn't moving faster than it's capable of moving. The rules simply don't apply to the stretching of the sheet itself. During the inflationary epoch, this principle manifested in the most extreme way imaginable. Space expanded so rapidly that points within the infant universe moved apart from each other faster than light could travel between them. Yet no information, no particle, no signal violated Einstein's speed limit. Everything respected the local laws of physics. It was space itself that grew with such ferocity that it outpaced even light's swift journey. The mathematics of this expansion are both elegant and violent. We describe the expansion of space using something called the scale factor, a number that tells us how much space has grown over time. During inflation, this scale factor didn't just increase, it increased exponentially, meaning it doubled again and again at a constant rate. Every tiny fraction of a second, the universe became twice as large, then twice as large again, and again, and again. There is a certain terror in exponential growth, a kind of mathematical horror that emerges when you truly contemplate what it means. Start with a penny and double it 30 times. You'd have more than $5 million. Double it 30 times more, and you'd have more wealth than currently exists on Earth. Double it another 30 times, and you'd have a number so large it ceases to have meaning in human terms. During inflation, space doubled not 30 times, not 60 times, but perhaps 100 times or more, in a period far shorter than it takes light to cross the diameter of a proton. As we drift deeper into this mystery, we must confront another strange implication. During inflation, different parts of the universe were expanding away from each other faster than light, which means they couldn't see each other, couldn't influence each other, couldn't exchange information. Regions of space became causally disconnected, cut off from each other by the sheer speed of expansion. Light emitted from one region would never catch up to another region because space was expanding too quickly. They were, in effect, in separate universes, islands of causality surrounded by an exponentially growing ocean of space-time. And yet, and this is crucial, these regions had all been in contact before inflation began. When the universe was in its initial tiny state, smaller than an atom, every point was in causal contact with every other point. They had a time to reach thermal equilibrium, to come to the same temperature, to share information. Then, inflation stretched them apart so rapidly that they lost contact, but they retained the memory of that initial connection. They remained synchronized, like clocks set in the same room, and then carried to opposite ends of the galaxy. This is how inflation solves the horizon problem. The regions we see on opposite sides of the sky, which appear never to have been in contact in the standard Big Bang model, were actually in intimate contact before inflation stretched them apart. They had time to coordinate, to reach the same temperature, to establish the same properties. Then inflation took over, expanding space so rapidly that these regions were separated by distances greater than light could cross, preserving their initial uniformity as the universe evolved. Perhaps the most beautiful aspect is how this expansion preserved quantum fluctuations, tiny, microscopic ripples in the fabric of space-time itself. These quantum jitters, which would normally remain confined to subatomic scales, were stretched by inflation to cosmic proportions. Imagine taking a photograph and enlarging it not just to poster size, not just to billboard size, but to galactic scales. The tiniest features, the individual grains of film, become vast cosmic structures. During inflation, quantum uncertainty became classical reality. Microscopic possibilities became macroscopic actuality, and the seeds of all future galaxies were sown. Yet this is only the beginning of the story. We've described what happened during inflation, but we haven't yet explored why it happened. What drove this exponential expansion? What engine powered the most dramatic transformation in cosmic history? To answer these questions, we must turn our attention to something even stranger than expanding space: the nature of the vacuum itself and the energy hidden within empty space. In the quiet depths of quantum field theory, there exists a concept so paradoxical, so contrary to common sense, that it took decades for physicists to fully accept its implications. Empty space, the vacuum, the void, the absence of everything, is not empty at all. It seethes with energy, vibrates with possibility, and under the right circumstances, can drive the most explosive transformation the universe has ever known. When we think of energy, we typically think of things: moving particles, hot objects, electromagnetic fields. We imagine energy as a property that matter possesses, something that requires the presence of stuff to exist. But quantum mechanics teaches us something stranger. Even when you remove all particles, all radiation, all matter from a region of space, the quantum fields themselves remain, and these fields possess energy. Not just a little energy, but potentially enormous amounts of it, locked away in what physicists call the vacuum state. But here's where the story becomes truly bizarre. There is not one vacuum state, but many. Think of a ball resting in a valley between hills. The ball has potential energy based on its height. Now, imagine a landscape with many valleys at different heights. A ball in a high valley has more potential energy than a ball in a low valley. Even though both are at rest, both are in stable positions. Quantum fields can exist in analogous states, different vacuum configurations, with different amounts of energy stored in the fabric of space itself. Before inflation, the universe found itself in what physicists call a false vacuum, a high-energy state that was temporarily stable, but not the lowest energy configuration possible. Imagine balancing a pencil perfectly on its point. For a moment, it might stay upright, apparently stable, but the slightest perturbation will send it falling to a lower energy state. Lying flat on the table, the false vacuum was like that pencil, stable for a brief moment, but inevitably destined to decay into a lower energy state. The energy stored in this false vacuum had a remarkable property. It generated a repulsive gravitational effect. In Einstein's general relativity, not only mass, but also energy and even pressure contribute to gravity. Positive pressure, the kind we're familiar with, generates attractive gravity, but negative pressure, which sounds impossible, but emerges naturally from certain quantum fields, generates repulsive gravity. The false vacuum possessed negative pressure, and this negative pressure drove the exponential expansion we call inflation. There is something profoundly calming about contemplating this moment, this stillness before the storm. The universe was small, perhaps smaller than we can meaningfully describe, and it was filled with this strange false vacuum energy. Nothing was happening, in a sense. There were no particles yet, no light, no motion as we understand it, just space, pregnant with potential, suffused with energy that would soon be released in the most dramatic transformation imaginable. The mathematical description of this state involves something called the inflaton field, a hypothetical quantum field that permeated all of space and sat temporarily at a high energy value. Like our pencil, balanced on its point, the inflaton field was in an unstable equilibrium. Quantum fluctuations, the inherent uncertainty and jitter that exists at microscopic scales, eventually pushed the field away from this unstable configuration, and when it began to roll down to its true vacuum state, inflation began. As the inflaton field began its journey from high to low energy, the energy stored in the false vacuum drove space to expand exponentially. The field itself changed slowly, in some models, excruciatingly slowly, but during this slow roll, the vacuum energy remained roughly constant, and this constant energy density caused space to expand at an exponential rate. Every fraction of a second, the universe doubled in size, then doubled again, and again. The expansion fed on itself, each moment creating more space, each new space carrying its own vacuum energy, driving further expansion. Yet this is only the beginning of the story. The false vacuum state was unstable, a temporary plateau on the energy landscape. Eventually, the inflaton field would roll down to its true, lowest energy state, and when it did, all that stored vacuum energy would be released. The transition from false vacuum to true vacuum would not be gentle. It would be a transformation of cosmic proportions, a phase transition, like water freezing to ice, but occurring throughout the entire universe simultaneously. The calming beauty of this picture lies in its inevitability. Once the inflaton field began its descent from the false vacuum, everything that would follow, the end of inflation, the reheating of the universe, the production of all the particles and radiation that would eventually form galaxies and stars and planets. All of this was written into the mathematics, encoded in the energy landscape of the quantum field. The universe didn't require fine-tuning or cosmic coincidence. It simply required a quantum field sitting in a high energy state, waiting to fall. And when it fell, when the inflaton field reached its lowest energy state, and inflation came to an end, all that stored energy had to go somewhere. The energy that had been driving the exponential expansion of space couldn't simply disappear. Energy is conserved even in the violent birth of the universe. Instead, it was converted into particles and radiation through a process called reheating, and the universe suddenly became hot, dense, and filled with the primordial soup of particles that would later cool and condense into all the matter we see around us. As we drift deeper into this mystery, we begin to see how inflation transforms our understanding of the Big Bang itself. The traditional Big Bang, the hot, dense state from which the universe emerged, was not the beginning. It was the aftermath, the consequence of inflation's end. The true beginning, if we can speak of such a thing, was stranger and quieter, a tiny region of space in a false vacuum state, poised on the edge of transformation, waiting for quantum uncertainty to give it the gentlest of pushes toward its destiny. Meanwhile, Across the vast expanse of scientific history, a young cosmologist was about to have an insight that would change everything. In December of 1979, Alan Guth sat in his office, working through the mathematics of phase transitions in the early universe, and suddenly realized that he had stumbled onto something extraordinary, a mechanism that could solve the horizon problem, the flatness problem, and the monopole problem all at once. He wrote in his notebook that night that this insight was spectacular, and indeed it was. But the road from inspiration to fully developed theory would prove longer and stranger than anyone imagined, and the implications of inflation would continue to surprise us even today. On a cold December night in 1979, in a modest office at the Stanford Linear Accelerator Center, a young physicist named Alan Guth was wrestling with a problem that had nothing to do with cosmology. He was thinking about magnetic monopoles, those hypothetical particles that grand unified theories predicted should exist in abundance, but which stubbornly refused to appear in any detector. The universe, it seemed, had found a way to avoid creating something that the mathematics said should be everywhere. But how? Guth had been exploring phase transitions in the early universe, moments when the cosmos underwent dramatic changes in its fundamental properties, like water suddenly freezing into ice. He was working through the details of a particular kind of phase transition called a first-order transition, characterized by the formation of bubbles of a new phase within the old phase, much like bubbles forming in boiling water. As he calculated, as he worked through the mathematics of how these bubbles would form and expand, something unexpected emerged from his equations. The energy associated with the phase transition, he realized, would cause space itself to expand exponentially, not gradually, not smoothly, but with a violence that would dwarf anything in the standard cosmological pictures. In this brief inflationary period, the universe would grow by an enormous factor, so enormous that any magnetic monopoles produced before inflation would be diluted to the point of invisibility. They wouldn't have disappeared. They would simply be so spread out, so thinned by the expansion of space, that we would never expect to find one in our observable universe. But as Guth stared at his calculations, he realized something even more extraordinary. This same mechanism, this exponential expansion, driven by a temporary high-energy state, would solve not just the monopole problem, but the other great cosmological puzzles as well. The horizon problem would evaporate because regions that now appear disconnected would have been in contact before inflation stretched them apart. The flatness problem would vanish because inflation would stretch space so dramatically that any initial curvature would be flattened out, like stretching a balloon until its surface appears perfectly flat. There is something almost musical about this moment of insight, this convergence of separate puzzles into a single elegant solution. Guth wrote in his notebook that night, in a moment of scientific euphoria, that this idea was spectacular, underlining the word with such force that his excitement remains visible on the page decades later. It was the kind of moment that every scientist dreams of, when seemingly unrelated problems suddenly reveal themselves to be different facets of the same underlying reality. Yet Guth understood that having an idea, however spectacular, was only the beginning. The path from inspiration to fully developed theory would require careful mathematics, rigorous checking, and the ability to make testable predictions. He would need to work out the details of exactly how inflation would begin, how it would proceed, and crucially, how it would end, because an inflationary universe that never stopped expanding would be just as problematic as the puzzles he was trying to solve. It would be a universe without matter, without structure, without the possibility of life. The original version of inflation that Guth proposed in his 1981 paper had what he called the graceful exit problem. The exponential expansion would begin easily enough, driven by the false vacuum energy, but it wouldn't stop smoothly. Instead, the universe would break up into separate bubbles, each transitioning to the true vacuum at different times, colliding with each other in ways that would create an inhomogeneous, chaotic cosmos. Nothing like the smooth, uniform universe we observe. It was a spectacular idea with a problematic ending, but Guth had opened a door, and other physicists rushed through it. Andre Linde in the Soviet Union, and Andreas Albrecht and Paul Steinhardt in the United States independently developed modifications to Guth's original proposal. Their new inflation solved the graceful exit problem by having the inflaton field roll more slowly and smoothly down its energy curve, allowing the phase transition to occur throughout space simultaneously rather than in separate bubbles. The mathematics became more refined, the predictions more concrete, and inflation transformed from a spectacular insight into a working scientific theory. As we drift deeper into this mystery, it's worth pausing to reflect on how science actually progresses. We often think of discovery as a single eureka moment, a flash of insight that reveals truth in its complete form. But the reality is more beautiful and more human. Guth's December night gave birth to a revolutionary idea, but it was incomplete, flawed, and in need of refinement. The theory that emerged over the following years was a collective creation built by many minds working together, each adding a piece, solving a problem, pushing the understanding forward. There is a certain humility in this recognition. Even the most brilliant insights require collaboration, criticism, and refinement. The universe does not reveal its secrets easily, even to those who ask the right questions. But when we work together, when we build on each other's ideas, rather than competing for individual glory, we can accomplish something remarkable. We can glimpse the universe's first moments, understand its violent birth, and find in the mathematics of fields and phase transitions an explanation for why we exist at all. Meanwhile, across the vast expanse of theoretical physics, the inflaton field itself, the mechanism that drove this spectacular expansion, would become the focus of intense study. What exactly was this field? Where did it come from? How did it interact with other fields? To answer these questions, we must drift into the realm of quantum field theory and discover how empty space can carry energy, how fields can drive cosmic evolution, and how the ghost in the machine of inflation might actually work. Picture, if you will, a field, not a field of grass or wheat, but something more fundamental, a mathematical entity that permeates all of space, existing at every point, carrying a value that can change over time. This is what physicists mean when they speak of a quantum field, and it is one of the most profound concepts in modern physics. The electromagnetic field is such a field, carrying the force that binds atoms and creates light. The Higgs field, discovered in 2012, is another, giving mass to fundamental particles through their interaction with it. And the inflaton field, though still hypothetical, is proposed to be the field that drove cosmic inflation, the ghost in the machine that powered the universe's most explosive transformation. But what does it mean for a field to drive expansion? How can something that sounds so abstract and mathematical have such concrete and dramatic effects on the fabric of space-time? The answer lies in one of the deepest principles of modern physics. Fields carry energy, and energy curves space-time. This is the essence of Einstein's general relativity. Mass and energy tell space-time how to curve, and the curvature of space-time tells matter and energy how to move. During inflation, the inflaton field's energy density was so enormous that it caused space itself to expand exponentially. The inflaton field is not like a particle sitting at a point in space. It exists everywhere, simultaneously, filling all of space with a certain energy value. Imagine a landscape, not a physical landscape with hills and valleys, but an abstract energy landscape where height represents energy. The inflaton field had a certain value at every point in space, and this value determined how much energy the field carried. During inflation, the field was stuck temporarily at a high point in this energy landscape, a false vacuum state where the energy density was enormous. This energy had a remarkable property, one that emerges naturally from quantum field theory, but seems almost magical when you first encounter it. Unlike ordinary matter, whose energy density decreases as space expands, think of gas molecules spreading out as a container grows larger. The inflaton field's energy density remained essentially constant during inflation. As space expanded, creating more volume, the field simply filled that new space with the same energy density. It was as if you could stretch a rubber band indefinitely, and it would maintain the same tension, a property that defies everyday intuition but follows naturally from the mathematics. There is something profoundly calming about contemplating how this works mathematically. In Einstein's equations, both the energy density and the pressure of a substance contribute to how space-time curves. For normal matter, pressure is positive and relatively small, but for the inflaton field in its false vacuum state, the pressure was not just negative, it was large and negative, exactly equal in magnitude to the energy density. This combination of positive energy density and negative pressure created a repulsive gravitational effect, causing space to expand exponentially rather than contracting under its own gravity, as intuition might suggest. The quantum nature of this field adds another layer of strangeness. At microscopic scales, quantum fields are never perfectly uniform. They fluctuate, jittering with quantum uncertainty in a way that cannot be eliminated, even in principle. Usually, these quantum fluctuations are confined to subatomic scales, too small to notice in everyday life. But during inflation, something extraordinary happened. The exponential expansion of space took these microscopic quantum fluctuations and stretched them to cosmic scales. Imagine drawing a tiny circle on a balloon and then inflating the balloon to the size of a planet. The circle grows, but more than that, its very nature changes. What was once a quantum fluctuation, a microscopic uncertainty in the value of the inflaton field, became a classical variation, a real difference in energy density from place to place. These stretched quantum fluctuations would later become the seeds of cosmic structure, the tiny density variations that would grow under gravity's influence to eventually form galaxies, clusters of galaxies, and the entire cosmic web of matter we observe today. As we drift deeper into this mystery, we must confront the fact that we still don't know what the inflaton field actually is. Unlike the electromagnetic field or the Higgs field, we haven't directly detected the inflaton. We've seen its effects, the flatness and uniformity of the universe, the pattern of density fluctuations in the cosmic microwave background. But we haven't identified it with any known fundamental field. It might be a completely new field, something beyond the standard model of particle physics. Or it might be something familiar, playing an unexpected role, perhaps related to the Higgs field, or to fields associated with grand unified theories. Multiple models of inflation exist, each proposing different energy landscapes for the inflaton field, different ways it might interact with other fields, different predictions for the detailed pattern of fluctuations it would create. Some models have the field rolling slowly down a gentle slope in the energy landscape. Others have it tumbling down steep cliffs. Some propose multiple fields working together, a complex choreography of quantum fields driving inflation through their interactions. The mathematics of these different models is rich and varied, but they all share the core insight. A field in a high energy state, coupled to gravity through Einstein's equations, will drive exponential expansion. Perhaps the most beautiful aspect is how the inflaton field connects quantum mechanics, the physics of the very small, to cosmology, the physics of the very large. The field itself is quantum mechanical, subject to uncertainty and fluctuation, but its effects are gravitational and cosmological, reshaping the entire universe. In inflation, we see the quantum and the cosmic dancing together, the microscopic uncertainty of field values becoming the macroscopic structure of galaxies and clusters. It is a bridge between two realms of physics that might otherwise seem forever separated. Yet this is only the beginning of the story. We've described what the inflaton field is and how it works, but we haven't yet fully explored what it means for space to double again and again at such an incredible rate. The mathematics of exponential growth is hypnotic, almost incomprehensible to minds that evolved to think linearly. And so, we turn our attention now to the numbers themselves, to the stunning arithmetic of a universe that grows by doubling and doubling and doubling again. There is something almost hypnotic about exponential growth, a quality that makes it both fascinating and terrifying to contemplate. We live in a world of linear intuition. If something grows by a fixed amount each step, we can easily imagine its future size. But when something doubles repeatedly, when each step multiplies what came before, our intuition fails us completely. The numbers become incomprehensibly large, faster than our minds can track, and we find ourselves in the presence of mathematical forces that reshape reality itself. During cosmic inflation, the universe underwent the most extreme example of exponential growth in history. Not growth by a fixed amount each moment, not even growth by a fixed percentage, but doubling, complete multiplication by 2, again and again, in impossibly brief intervals. Let us sit with this for a moment and truly try to grasp what it means. Imagine starting with something small, say, the size of a proton, roughly 10 to 15 meters. Now double it. You've reached 2x 10, 15 meters. Still unimaginably small. Double it again and again. After just 10 doublings, you've multiplied your initial size by about 1,000. The proton-sized beginning has grown to about 10 to 12 meters, the size of a large molecule. Interesting, but still invisible to the naked eye. Continue doubling. After 20 doublings, you've multiplied by roughly 1,000,000. After 30 doublings, by about 1 billion. After 40 doublings, by about 1 trillion. Now, your initial proton-sized region is approaching the size of a bacterium, 10 to 6 meters. We've doubled 40 times, and we're still dealing with microscopic scales. But watch what happens as we continue. After 50 doublings, we've multiplied by about a quadrillion, 1015. The original proton-sized region is now about a meter across, the size of a human. After 60 doublings, it's 1,000 kilometers wide, larger than Texas. After 70 doublings, it's 1 billion kilometers across, large enough to contain the entire inner solar system. We've gone from subatomic to solar system sized in just 70 doublings. But inflation didn't stop there. Depending on the specific model, inflation might have involved anywhere from 60 to 100 doublings, or possibly even more. Let's continue our journey. After 80 doublings, our original proton-sized region would be about 10 to 24 meters across, comparable to the size of our observable universe today. And inflation might have continued for another 20 doublings or more. Beyond this point, there is something profoundly calming about contemplating these numbers, even as they stretch our comprehension past the breaking point. Each doubling takes a period of time so brief that light, traveling at its maximum speed, can barely cross the distance of an atomic nucleus. The specific timescale depends on the model, but in many versions of inflation, the doubling time is around 10 to 37 seconds, a decimal point followed by 36 zeros, and then a 1. In less time than it takes light to cross from one side of a proton to the other, the entire universe doubles in size. The mathematical structure of exponential growth has a peculiar property. It doesn't matter what size you start with, whether you begin with a proton-sized region, an atom-sized region, or something even smaller. After the same number of doublings, you'll reach the same final ratio of growth. This is why inflation can take quantum fluctuations, variations in field values at the Planck scale, the smallest meaningful length scale in physics, around 10 to 35 meters, and stretch them to cosmic scales spanning billions of light years. The doubling doesn't care about absolute size. It only cares about multiplication. As we drift deeper into this mystery, we must confront another strange implication. Different regions of the inflating universe were doubling at the same rate, but they were becoming exponentially separated from each other. Imagine 2 points on a balloon's surface as it inflates. The farther apart they start, the faster they separate. During inflation, this effect was so extreme that regions of space could be separating faster than light could travel between them, not because anything was moving faster than light through space, but because space itself was expanding so rapidly. This created what physicists call horizons, boundaries beyond which information cannot pass because space is expanding too quickly. If you were somehow present during inflation, you wouldn't be. Of course, but let's imagine you would see a horizon surrounding you, a sphere beyond which you could see nothing, receive no signals, have no causal contact, and this horizon would be shrinking in physical size as space expanded. because new regions of space were constantly crossing out of your causally connected patch. The elegance of this mathematics reveals itself in the predictions it makes. The pattern of density fluctuations created by quantum jittering during inflation should have a specific form, what physicists call a nearly scale invariant spectrum. This means that fluctuations at different sizes should have nearly the same amplitude, with small, calculable deviations. When cosmologists measured the cosmic microwave background, radiation in exquisite detail, they found exactly this pattern. The predictions of exponential expansion, of quantum fluctuations stretched to cosmic scales, matched reality with stunning precision. Yet the numbers still stagger the imagination. Consider that the observable universe today, everything we can see with our most powerful telescopes, all the galaxies spanning 93 billion light years, originally fit into a region smaller than a proton before inflation began. Everything that would become the stars, the planets, the gas between galaxies, you and I, and every atom we're made of, all existed in a tiny patch of space that underwent at least 60 doublings, possibly 100 or more, in less than a second. Less than a second is already incomprehensibly brief for such transformation, but the actual duration was far shorter, perhaps 10 to 32 seconds, a time so small that a trillion of these intervals would fit into a single second. Perhaps the most beautiful aspect is the inevitability of it all. Once exponential expansion begins, once the doubling starts, the rest follows automatically from the mathematics. You don't need to invoke new physics at each step. Don't need to fine-tune parameters or adjust conditions. The equations simply carry you forward, doubling and doubling again, transforming the quantum into the cosmic through the blind operation of mathematical law. Meanwhile, across the vast expanse of time, or rather, across the infinitesimal fraction of a second, this exponential expansion couldn't continue forever. The inflaton field was rolling down its energy landscape, approaching the point where inflation would end and the universe would transition to a new phase. The mathematics that drove the doubling would soon give way to different physics, and the universe would undergo yet another transformation, perhaps equally dramatic, but completely different in character. And so we must now ask, how did inflation end? And what happened when it did? In the quiet depths of the inflationary epoch, after countless doublings had stretched the universe to unimaginable scales, something had to change. The inflaton field could not remain forever in its false vacuum state, driving exponential expansion into eternity. Like our metaphorical pencil balanced on its point, the field was destined to fall, to roll down the energy landscape toward its true minimum. And when it did, when inflation finally ended, the universe would undergo a transformation as dramatic as inflation itself, though of a completely different character. The end of inflation is often called reheating, a term that sounds almost gentle, but describes a violent conversion of energy from one form to another. During inflation, the energy of the universe was locked up in the inflaton field itself, stored in the false vacuum state that permeated all of space. There were no particles, no radiation, no heat, just space expanding exponentially, driven by field energy. But as the inflaton field rolled down its energy curve and reached the true vacuum state, all that enormous energy had to go somewhere. What happened was something like a cosmic phase transition, similar to water, freezing into ice but occurring throughout the entire universe. Nearly simultaneously, the inflaton field began to oscillate rapidly around its minimum energy value, like a marble rolling back and forth in a bowl. These oscillations caused the field to decay, to transfer its energy into other quantum fields, producing particles and antiparticles in enormous quantities. It was as if the universe suddenly remembered how to make matter. There is something almost musical about this process, a cosmic symphony where the solo instrument of the inflaton field gives way to a full orchestra of particle fields, quarks and antiquarks, electrons and positrons, photons and neutrinos. All the fundamental particles of nature came flooding into existence, created from the pure energy of the decaying inflaton field. The universe, which moments before had been cold and empty, save for the inflaton itself, suddenly became hot and dense, filled with a primordial soup of particles, colliding and interacting and creating the complexity that would eventually lead to atoms, molecules, stars, and life. The temperature reached during reheating was likely incomprehensibly high, perhaps 1027 degrees Kelvin or more, trillions of times hotter than the core of the sun. At such temperatures, matter as we know it cannot exist. Protons and neutrons break apart into their constituent quarks. Even the vacuum of space itself becomes a seething foam of virtual particles, created and destroyed in quantum fluctuations so violent that they temporarily curve space-time on microscopic scales. The universe had become what physicists poetically call the primordial fireball, the hot, dense state that we traditionally think of as the Big Bang. But here's the profound shift in perspective that inflation brings. This hot Big Bang, this fireball of particles and radiation, was not the beginning. It was the aftermath, the consequence of inflation's end. The true beginning, if we can speak of such a thing, was the cool, empty, exponentially expanding space-time of the inflationary epoch. The Big Bang, as traditionally conceived, was really the big reheating, the moment when the energy of inflation was converted into matter and radiation. As we drift deeper into this mystery, we must appreciate how inflation solved the fine-tuning problems that plagued the original Big Bang model. The horizon problem vanished because regions that appeared never to have been in causal contact had actually equilibrated before inflation stretched them apart. The flatness problem disappeared because inflation stretched space so dramatically that any initial curvature was flattened to the point of invisibility, and the monopole problem was resolved because any monopoles produced before inflation would have been diluted to essentially zero density by the exponential expansion. The elegance of this solution lies in its simplicity. One mechanism, exponential expansion, driven by a scalar field in a high-energy state, solved multiple, seemingly unrelated problems simultaneously. It transformed the initial conditions from something that required precise fine-tuning to something that could arise naturally from quantum field dynamics. The universe didn't need to start in a special state. It just needed a field in a false vacuum, and quantum mechanics and gravity would take care of the rest. Yet the graceful exit from inflation was not guaranteed from the beginning. Guth's original model had the inflaton field trapped in the false vacuum by energy barriers, and when the field finally tunneled through these barriers, it would do so at different places, at different times, creating bubbles that would collide chaotically. This didn't match the smooth, uniform universe we observe. The new inflation models developed by Linde, Albrecht, and Steinhardt solved this by having the field roll smoothly and slowly down a gentle slope, allowing it to end inflation everywhere at nearly the same time. The details of how reheating occurred depend on the specific model of inflation, on the shape of the inflatant's energy landscape, and on how the inflatant field couples to other quantum fields. In some models, reheating is nearly instantaneous. The field oscillates and decays rapidly, converting its energy to particles in a fraction of a second. In other models, reheating is more gradual, with the universe expanding and cooling even as particles are being produced. But in all models, the result is the same: a hot, dense, expanding universe filled with matter and radiation, evolving according to the well-understood physics of the standard Big Bang cosmology. Perhaps the most beautiful aspect is how this connects the quantum and the cosmic, the microscopic and the macroscopic. Quantum fluctuations during inflation, stretched to cosmic scales, became the density perturbations that seeded galaxy formation. The quantum decay of the inflaton field produced all the particles that would eventually form stars and planets and life. The quantum nature of fields themselves, their ability to carry energy, to oscillate, to interact, drove the universe's most dramatic transformations. In the story of inflation and reheating, we see quantum mechanics not as an abstract mathematical formalism, but as the engine of cosmic evolution, the mechanism by which possibility becomes actuality on the grandest scales imaginable. And so, the universe emerged from inflation transformed, no longer tiny and cold, but vast and hot, no longer dominated by field energy, but filled with particles and radiation, no longer exponentially expanding, but following the more sedate expansion of the standard Big Bang. The stage was set for everything that would follow: the formation of atomic nuclei in the first few minutes, the emergence of atoms after 380,000 years, the gravitational collapse of those atoms into the first stars and galaxies. All of this became possible because inflation ended, because the inflaton field completed its graceful exit and bequeathed its energy to the matter and radiation that would build the cosmos we know today. Now that we've witnessed the dramatic exit from inflation and the birth of the hot Big Bang, let us return to one of the deepest mysteries that inflation was designed to solve. Look up at the night sky and imagine drawing a line from horizon to horizon, passing directly through your head. The light reaching your eyes from opposite ends of this line has traveled for 13.8 billion years to reach you, crossing the entire observable universe. These photons set out on their journey when the universe was young, hot, and simple, and they have been traveling ever since through the expanding cosmos. When cosmologists measure the temperature of this ancient light, the cosmic microwave background radiation, from opposite sides of the sky, they find something remarkable. The temperatures match to within 1 part in 100,000. These distant regions, separated by such vast distances that light has never had time to travel between them in the entire history of the universe, somehow possess exactly the same temperature, the same density, the same properties. It is as if two violinists on opposite sides of Earth who have never met or communicated are playing exactly the same note at exactly the same moment. In the standard Big Bang model, without inflation, this uniformity was simply inexplicable. The regions we see on opposite sides of the sky have been outside each other's light cones since the beginning. They are causally disconnected, meaning no signal, no information, no physical influence could have traveled between them. How then did they coordinate? How did they agree on what temperature to be, what density to have, what laws of physics to follow? The mathematics seemed to demand that we accept this uniformity as an initial condition, a cosmic coincidence that we could observe but never explain. There is something deeply unsatisfying about this kind of explanation, or rather, this lack of explanation. Science progresses by finding causes for effects, by tracing the present back through chains of causation to understand why things are the way they are. To simply declare that the universe began in a uniform state without explaining why feels like giving up, like admitting defeat before the battle has truly begun. And yet, in the standard Big Bang cosmology, there seemed no alternative. But inflation transforms this picture completely. Before inflation began, when the universe was unimaginably small, far smaller than an atom, smaller than a proton, smaller perhaps than anything we can meaningfully describe, all of what would become our observable universe was compressed into a tiny region where every point was in causal contact with every other point. At this primordial moment, physical processes could operate, heat could flow, quantum fields could equilibrate, information could pass from place to place at the speed of light. And since the entire future observable universe occupied such a minuscule volume, light had plenty of time to cross it many times over. During this brief period before inflation, the universe reached thermal equilibrium, a state where temperature, density, and field values became uniform throughout this tiny patch. It's the same process that occurs when you leave a cup of hot coffee on a table. The coffee cools, the surrounding air warms, and eventually everything reaches the same temperature. In the infant universe, quantum processes ensured that the entire tiny patch, everything that would later become billions of galaxies spanning billions of light years, came to the same temperature, the same density, the same configuration of quantum fields. Then inflation began. In less than a second, perhaps in far less than 10 to 32 seconds, this tiny uniform patch was stretched by a factor of at least 1026, possibly much more. Points that had been neighboring, sharing information freely, suddenly found themselves separated by distances so vast that light would need billions of years to travel between them. The exponential expansion of space tore apart the causal connections, but preserved the initial uniformity, like taking a photograph of a uniform surface and enlarging it to cosmic dimensions. Inflation stretched the initial equilibrium state across the entire observable universe. As we drift deeper into this mystery, we can see how elegant and natural this solution is. The regions on opposite sides of our sky have the same temperature, not because of some cosmic coincidence, not because the initial conditions happened to be fine-tuned, but because they were once close enough to touch, close enough to exchange heat and reach equilibrium. Inflation didn't create the uniformity. It preserved and amplified uniformity that had already been established through ordinary physical processes operating in an extraordinarily small volume. The mathematics of this is both simple and profound. In the standard Big Bang model, the particle horizon, the maximum distance that light could have traveled since the beginning, is smaller than the distance between regions we observe to have the same temperature. This creates an impossible situation: causally disconnected regions somehow coordinating their properties. But with inflation, the calculation changes completely. The particle horizon in the pre-inflationary era is large enough to encompass the entire region that would later become our observable universe. Causal contact was possible before inflation, and the uniformity we observe is simply the stretched out remnant of that primordial equilibrium. There is something profoundly calming about this realization. The universe is not fine-tuned or mysteriously coordinated. It is simply the natural consequence of well-understood physical processes: thermal equilibrium, quantum field dynamics, and exponential expansion driven by negative pressure, operating in a specific sequence. The horizon problem, which seemed to require either divine intervention or cosmic coincidence, turned out to be no problem at all once we understood that the universe had a pre-inflationary history, however brief, during which ordinary causal processes could operate. Yet this is only one of the puzzles that inflation resolves. Another equally deep mystery concerns the geometry of space itself, the curvature of the universe on the largest scales. And here too, inflation provides an explanation so elegant that it seems almost inevitable once you see it. But to understand this solution, we must first understand the puzzle of flatness and why the geometry of the universe seems to have been adjusted with impossible precision. There is something almost musical about the geometry of the universe, a mathematical harmony that reveals itself when we measure how space curves on the largest scales. Einstein's general relativity teaches us that the universe can have one of three possible geometries. It can curve back on itself, like the surface of a sphere, creating what mathematicians call positive curvature. It can curve away from itself, like a saddle, creating negative curvature. Or it can be perfectly flat, like an infinite plane, extending in all directions with zero curvature. The geometry depends on the density of matter and energy in the universe. Too much density and space curves positively, eventually closing back on itself. Too little and space curves negatively, expanding forever in an open hyperbolic geometry. Exactly the critical density and space is flat. When cosmologists began measuring the geometry of our universe, they found something that should have been surprising, but instead felt almost eerie. The universe is flat, or very nearly so. The measurements are now precise enough to say that if the universe has any curvature at all, it is less than about 1% deviation from perfect flatness. On the largest scales we can observe, space appears to be Euclidean. Parallel lines remain parallel. The angles of triangles sum to 180 degrees, and the universe extends infinitely without curving back on itself. But here's the profound puzzle. Flatness is unstable in the standard Big Bang model. Imagine trying to balance a pencil on its point. If you get it exactly vertical, it might stay balanced for a moment. But the slightest deviation, a tiny tilt of even a fraction of a degree, will send it tumbling to the table. The deviation grows over time. The pencil moves farther and farther from vertical as it falls. Flatness in the expanding universe behaves similarly. A universe that starts out flat will remain flat, but one that starts with even The tiniest curvature will become more curved as it evolves. The mathematics of this instability is both elegant and troubling. The ratio of the actual density to the critical density, what cosmologists call omega O, characterizes the curvature. If O equals exactly 1, the universe is flat. If O is greater than 1, space has positive curvature, less than 1, negative curvature. In the standard Big Bang model, if O starts out even slightly different from 1, it evolves away from 1 over time. The deviation grows as the universe expands, like our pencil falling from vertical. For the universe to be as flat as we observe today, with O within 1% of 1 after 13.8 billion years of expansion, it would have needed to be extraordinarily flat in the early universe. When cosmologists work backward, calculating what O must have been in the first second after the Big Bang to produce today's near flatness, they arrive at a number that staggers the imagination. O must have equaled 1 to within 1 part in 1015 at 1 second, and to within 1 part in 1060 at the Planck time, the earliest moment we can meaningfully discuss. There is a certain terror in such precision, a sense that we're confronting something that requires explanation rather than acceptance. 1 part in 1060 is not merely fine-tuning, it is hyper-fine-tuning, adjustment to a level of precision that makes the finest watchmaker seem clumsy, that exceeds any mechanism we know in physics. If the initial density had been off by the tiniest fraction, by 1 part in 1060, the universe would either have collapsed back on itself within microseconds or expanded so rapidly that no structures could ever form. No stars, no galaxies, no planets, no life. We exist, it seemed, balanced impossibly on the knife's edge of cosmic geometry. But inflation dissolves this puzzle with elegant simplicity. During exponential expansion, any initial curvature is stretched flat, like inflating a balloon, until its surface appears perfectly planar. Consider a sphere, say, the Earth. On small scales, the surface is obviously curved. Stand in one place, and you can see the horizon curving away from you. But imagine inflating the Earth until it's the size of the entire observable universe. Now stand on its surface. The curvature would be so gentle, the radius so enormous, that the surface would appear perfectly flat to any measurement you could make. This is what inflation does to the geometry of space. The mathematical description is straightforward. The curvature of space scales as 1 over the square of the scale factor. If the universe expands by a factor of 1026 during inflation, a modest estimate, then the curvature decreases by a factor of 1052. Any initial curvature, no matter how large, becomes negligible after such exponential expansion. The universe is driven toward flatness, not by fine-tuned initial conditions, but by the dynamics of inflation itself. Flatness is not a coincidence, it is a prediction. As we drift deeper into this mystery, we see how this solution connects to the horizon problem. Both puzzles arise from the same source. In the standard Big Bang model, the universe doesn't have enough time to establish the properties we observe. Regions don't have time to thermalize, and curvature doesn't have time to flatten. But inflation provides that time, or rather, provides the mechanism to stretch an initially small, equilibrated, possibly highly curved region into something vast, uniform, and flat. There is something profoundly calming about this realization. The flatness of the universe is not a cosmic accident, not a miracle of fine-tuning. It is simply what happens when space undergoes exponential expansion. The pencil doesn't need to be balanced perfectly because inflation is constantly pushing it back toward vertical, constantly flattening any curvature that might exist. After sufficient inflation, the universe emerges flat regardless of how it began. This has deep implications for how we think about initial conditions in cosmology. Before inflation, cosmologists worried that they needed to explain why the universe started in such a special state: flat, uniform, smooth. After inflation, these properties emerge naturally from the dynamics. The initial state before inflation could have been curved, inhomogeneous, chaotic. Inflation would smooth it out, flatten it, and make it uniform. The universe doesn't require fine-tuned beginnings. It requires only inflation. Yet even as inflation solves the flatness problem, it creates another layer of mystery. If inflation flattens the universe so effectively, why did it stop when it did? Why didn't it continue forever, stretching space until the density became infinitesimally small and the universe was essentially empty? The answer relates to how the inflaton field rolled down its energy landscape, but it also opens up more profound questions. And before we explore those, we must first understand one of inflation's most beautiful predictions: how quantum uncertainty at the smallest scales became the cosmic structure at the largest scales, how microscopic fluctuations seeded all the galaxies we see around us. Picture, if you will, a perfectly smooth universe, space-time stretching in all directions with absolutely no variation in density, temperature, or field values from one point to another. Such a universe would be beautiful in its simplicity, elegant in its uniformity, but it would also be lifeless, sterile, incapable of producing any structure or complexity. Galaxies require variations in density to form. Gravity needs regions that are slightly denser than average to pull matter together. Without some initial lumpiness, some primordial seeds around which matter could collect, the universe would remain forever smooth and empty, a vast ocean without waves, a canvas without texture. The universe we inhabit is not smooth. It is magnificently structured, with galaxies clustered into groups and clusters. These clusters forming superclusters, and the superclusters arranged in vast filaments and walls surrounding enormous voids. The cosmic web, as astronomers call it. This structure exists because the early universe was not perfectly uniform. It had tiny density variations, small regions that were slightly denser or slightly less dense than average. These variations, though minuscule, were enough for gravity to amplify over billions of years, pulling matter toward the denser regions and creating the large-scale structure we observe today. But where did these density variations come from? In the standard Big Bang model, they simply had to be assumed as initial conditions. Another fine-tuning problem, another aspect of the universe that required explanation but received none. The variations needed to be of just the right amplitude, about 1 part in 100,000, and have just the right pattern, slightly larger amplitude at larger scales, to produce the universe we see. Why should the universe begin with precisely these properties? Inflation provides an answer, and it is one of the most beautiful connections between quantum mechanics and cosmology ever discovered. The density variations we observe originated as quantum fluctuations during the inflationary epoch. At the quantum level, nothing is perfectly smooth. Heisenberg's uncertainty principle tells us that fields must fluctuate, jittering randomly around their average values. Usually, these fluctuations are confined to microscopic scales, subatomic, invisible, irrelevant to the large-scale world. But during inflation, something extraordinary occurred. The exponential expansion of space took quantum fluctuations and stretched them to cosmic scales, transforming microscopic uncertainty into macroscopic reality. Imagine the inflaton field during inflation as a gently rippling surface, like a pond with tiny wavelets stirred by quantum uncertainty. At any moment, the field value might be slightly higher in one region, slightly lower in another, with these variations occurring at the smallest possible scales. The Planck length, around 1035 meters. In any other context, such minuscule fluctuations would be utterly irrelevant, washed out by thermal noise, or simply too small to notice. But during inflation, these quantum ripples were stretched, along with space itself, as a particular quantum fluctuation crossed outside the horizon during inflation. As it grew larger, then the distance light could travel in the brief moment of inflation. It became frozen, locked into the fabric of space as a classical density perturbation. The quantum uncertainty, which exists in a superposition of possibilities at microscopic scales, underwent something like measurement by the expansion of space itself, collapsing into a definite classical variation. Wave after wave of quantum fluctuations crossed the horizon as space expanded, each becoming a frozen density perturbation at the scale where it exited the horizon. There is something profoundly calming about contemplating this process, this transformation of quantum uncertainty into cosmic structure. The galaxies we see, the clusters and superclusters, the vast cosmic web, all of it traces back to quantum jitter in the inflaton field during the first fraction of a second. The Andromeda Galaxy exists because of a quantum fluctuation. The cluster of galaxies containing the Milky Way formed around a density perturbation that originated in quantum uncertainty. Every structure in the universe, from the smallest dwarf galaxy to the largest supercluster, began as a microscopic quantum ripple that inflation stretched to cosmic proportions. The mathematics of this process makes specific, testable predictions. The amplitude of fluctuations should be nearly the same at all scales, with small deviations that depend on exactly how the inflaton field rolled down its energy landscape. The fluctuations should have a Gaussian distribution. Their statistical properties should match those of random quantum noise, and they should be adiabatic, meaning density. Variations should be accompanied by corresponding temperature variations in a specific way. When cosmologists measured the cosmic microwave background with increasing precision, first with the COBE satellite in the 1990s, then with WMAP in the 2000s, and most recently with Planck, they found exactly the pattern predicted by inflation. The fluctuations had the right amplitude, about 1 part in 100,000. They had the right statistical properties, consistent with quantum randomness. They followed a nearly scale-invariant spectrum with slightly more power at larger scales, exactly as predicted by simple models of inflation. The quantum seeds had been found, and they matched the theoretical predictions with stunning accuracy. As we drift deeper into this mystery, we must appreciate the profound philosophical implications. The universe is structured because of quantum uncertainty, because Heisenberg's principle forbids perfect smoothness at the smallest scales. If quantum mechanics allowed perfectly definite field values, if the inflaton could have been exactly constant throughout space during inflation, then the universe would have emerged from inflation perfectly smooth and would have remained smooth forever. No galaxies, no stars, no planets, no life. We exist because quantum mechanics is fundamentally uncertain, because fields must fluctuate, because perfect knowledge is impossible even in principle. Moreover, the spectrum of fluctuations carries information about the inflationary epoch itself. By measuring the precise pattern of hot and cold spots in the cosmic microwave background, cosmologists can infer properties of inflation: how fast the inflaton field was rolling, what the energy scale of inflation was, how long inflation lasted. The early universe has left us a message written in the statistical properties of density fluctuations, and we are learning to read it. Yet perhaps the most beautiful aspect is the universality of this mechanism. It doesn't depend on the specific details of the inflaton field or the precise model of inflation. Any period of exponential expansion driven by a quantum field will stretch quantum fluctuations to cosmic scales. Any inflation produces density perturbations. The galaxies are not an accident, not a special feature of our particular universe, but an inevitable consequence of quantum physics and exponential expansion working together. This universality, however, raises deeper questions. If inflation is so robust, so inevitable once it begins, might it continue in some regions even after ending in others? Could inflation be an eternal process, constantly creating new regions of space while ending in others? These questions lead us to one of the most profound and speculative implications of inflation: the possibility that our universe is just one bubble in an eternally inflating multiverse, and that the process of cosmic creation never truly ends. In the quiet depths of inflationary theory lies a paradox that challenges our very concept of universe and beginning. We have described inflation as a process that starts, runs its course through exponential expansion, and then ends when the inflaton field reaches its true vacuum state, reheating the universe and producing the hot Big Bang. But the quantum nature of the inflaton field adds a twist to this story, one that suggests inflation might never truly end, at least not everywhere at once. The paradox arises from the same quantum fluctuations that seeded galaxies during inflation. The inflaton field is rolling down its energy landscape toward the true vacuum, but quantum mechanics says that fields must fluctuate, and sometimes these fluctuations push the field upward, back toward higher energies, rather than downward. Most regions of space will see the field roll steadily downward, ending inflation and reheating to produce a hot Big Bang universe like ours. But some regions, due to quantum fluctuations, will see the field jump to higher values, and in those regions, inflation continues. Imagine a ball rolling down a hill. On average, gravity pulls it downward, and it will eventually reach the bottom. But now imagine that quantum uncertainty gives the ball occasional random kicks. Most of the time, these kicks don't matter much. The ball continues rolling downward, but occasionally, a kick pushes the ball back upward, and it must roll down the hill again. Now imagine this happening not to one ball, but to all of space, different regions experiencing different quantum kicks. some ending inflation, while others continue inflating. The mathematics of this process leads to a startling conclusion. If the upward quantum jumps occur faster than the downward rolling in any region, then that region will expand exponentially forever, constantly producing new space that is still inflating. Even though most regions will eventually stop inflating, the inflating regions grow so much faster than the non-inflating regions that the total volume of space that is inflating actually increases with time. Inflation, once begun, becomes eternal, not in the sense that it lasts forever everywhere, but in the sense that it never stops completely, always continuing in some expanding regions. This is eternal inflation, and it transforms the picture of cosmic creation into something far stranger than we initially imagined. Our observable universe, everything we can see, all the galaxies out to the edge of our cosmic horizon, would be just one bubble in an infinite foam of bubbles, each bubble forming when inflation ended in some region and reheated to produce a hot Big Bang universe. Beyond our bubble, space is still inflating exponentially, producing more bubbles, which themselves are surrounded by still inflating space, producing yet more bubbles in an endless, fractal cascade of cosmic creation. There is something both terrifying and beautiful about this picture. Terrifying because it suggests that what we call the universe, everything we can observe or ever hope to observe, is just one bubble among an infinite number of bubbles, each potentially with different properties, different physical laws, different constants of nature. Beautiful because it reveals creation as an ongoing process rather than a one-time event, a cosmos that is constantly giving birth to new universes, each one a separate world with its own history and destiny. As we drift deeper into this mystery, we must confront the unsettling implications for causality and observation. Other bubbles in the eternal inflation scenario are forever beyond our reach. They are not just far away in the sense that we'd need a faster spaceship to reach them. They are causally disconnected from us in the most fundamental sense, separated by regions of eternally inflating space that expand faster than light can cross them. We can never see them, never visit them, never exchange information with them. They are separate universes in the most complete meaning of that word. Moreover, different bubbles might emerge from inflation with different properties. The constants of nature, the strength of gravity, the mass of the electron, the speed of light might vary from bubble to bubble if these constants depend on how fields settle into their lowest energy states at the end of inflation. In some bubbles, the constants might allow for the formation of stars and galaxies and life. In others, the constants might be such that no complex structure can form. We find ourselves in a bubble where conditions permit our existence, not because of cosmic fine-tuning, but because of anthropic selection. We exist in a bubble where existence is possible because we couldn't find ourselves in a bubble where it's not. The philosophical implications ripple outward like waves from a stone dropped in a pond. The question, why is the universe the way it is, transforms from a question about initial conditions to a question about the landscape of possible universes. Perhaps every possible way a universe could be exists somewhere in the eternally inflating multiverse, and we observe the particular properties we do simply because those are the properties compatible with observers existing to ask questions. Yet this very richness creates scientific challenges. If eternal inflation produces every possible universe, does it really predict anything? Can we test a theory that seems to explain everything by predicting a multiverse so vast and varied that any observation we make will be realized somewhere? Physicists debate whether eternal inflation is a profound insight or a retreat from falsifiability, whether it represents the culmination of inflation theory or exposes a weakness in our ability to make definite predictions. Perhaps the most beautiful aspect is how eternal inflation connects back to where we began, with quantum uncertainty. The quantum fluctuations that prevent inflation from ending everywhere simultaneously are the same fluctuations that seeded galaxies in our own bubble universe. Quantum mechanics, which operates at the smallest scales, determines the fate of the largest structures imaginable. The multiverse itself, the microscopic and the cosmic, are inextricably linked, bound together by the mathematics of field theory and the logic of exponential expansion. There is something profoundly calming about accepting the limits of what we can know. If eternal inflation is correct, most of reality is forever beyond our observational reach. We are confined to our bubble, able to see only a finite patch of space where inflation happened to end around the same time. Beyond that lies mystery, not the kind of mystery we might someday solve with better instruments, but fundamental mystery encoded in the structure of space-time itself. Some questions about the cosmos might be answered not by observation, but by logical inference, mathematical consistency, and philosophical reflection. And yet, even within our bubble, even within the finite patch of space accessible to observation, inflation makes predictions we can test. The flatness and uniformity of the observable universe, the spectrum of density fluctuations, and potentially, if we are fortunate, the signature of gravitational waves produced during inflation itself. These predictions anchor inflation to the realm of testable science, even as eternal inflation leads us to speculate about the untestable vastness beyond. Meanwhile, across the vast expanse of both space and scientific inquiry, researchers continue to search for these predictions in the cosmos around us. The cosmic microwave background carries echoes of inflation, faint whispers of that primordial epoch written in the pattern of temperature fluctuations across the sky. And buried within these fluctuations might be an even more dramatic signal, the imprint of gravitational waves, ripples in space-time itself, produced by the violent expansion of the inflationary epoch. If we can find this signal, we will have direct evidence of inflation's reality and a window into the physics of the earliest moments of cosmic time. When you look up at the night sky, you see stars, points of light that have traveled for years, decades, or even millennia to reach your eyes. But between those stars, in the darkness that seems empty, there exists something far more ancient and far more profound, filling all of space, streaming from every direction, is the oldest light in the universe, the cosmic microwave background radiation, photons that have been traveling for 13.8 billion years, carrying with them echoes of the universe's first moments. This radiation was released when the universe was just 380,000 years old, a time when it had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque. Photons couldn't travel freely because they were constantly scattering off free electrons, like light trying to penetrate a thick fog. But when the electrons combined with protons, the fog suddenly cleared, and light could travel unimpeded across the cosmos. That light has been traveling ever since, stretched by the expansion of space from visible wavelengths into microwaves, cooled from thousands of degrees to just 2.7 degrees above absolute zero. What makes this ancient light precious to cosmologists is not just its age, but what it carries. The cosmic microwave background is not perfectly uniform. If you could see microwave radiation with your eyes, you would observe that the sky is slightly warmer in some directions and slightly cooler in others, with variations of about 1 part in 100,000. These tiny temperature differences are the fingerprints of inflation, the imprints of quantum fluctuations stretched to cosmic scales during the exponential expansion of the early universe. The pattern of these fluctuations tells a story, and cosmologists have learned to read it with exquisite precision. When a region of space is slightly denser than average, gravity compresses it, heating it up, and this shows up as a slightly warmer spot in the cosmic microwave background. When a region is slightly less dense, it appears cooler. The size of the hot and cold spots, their distribution across the sky, and their statistical properties all encode information about the primordial density fluctuations, the quantum seeds that inflation stretched from microscopic to cosmic scales. There is something almost musical about the way cosmologists analyze this pattern. They decompose the temperature map into what are called spherical harmonics, mathematical functions that describe patterns on a sphere, much like how musical notes can be decomposed into fundamental frequencies and overtones. The power spectrum of the cosmic microwave background, a graph showing how much fluctuation exists at each angular scale, is like a cosmic symphony with peaks and valleys that reveal the physics of the early universe. The first peak in this spectrum corresponds to sound waves in the primordial plasma, regions that were compressed by gravity and then pushed back by radiation pressure, creating acoustic oscillations. The position of this peak tells us about the geometry of the universe, confirming that space is flat, just as inflation predicts. The second and third peaks tell us about the ratio of ordinary matter to dark matter, about the density of baryons, about the subtle interplay of forces in the first few 100,000 years of cosmic history. But perhaps most importantly, the overall shape of the power spectrum, the way fluctuation amplitude varies with scale, matches precisely what inflation predicts. The spectrum is nearly scale invariant, meaning fluctuations have roughly the same amplitude at all scales, with a slight tilt that depends on how the inflaton field rolled down its energy landscape. When the Kobe satellite first measured this spectrum in the early 1990s, when WMAP refined the measurements in the 2000s, and when Planck produced the most detailed map yet in the 2010s, the match between theory and observation became increasingly stunning. As we drift deeper into this mystery, we must appreciate what a remarkable validation this represents. Inflation makes specific, quantitative predictions about the pattern of fluctuations imprinted on the cosmic microwave background. These predictions were made before the observations, not fitted to them after the fact. When the observations came in, they matched. The quantum fluctuations during inflation, the exponential expansion, the freezing of fluctuations as they crossed the horizon. All of this exotic physics occurring in the first fraction of a second, left its mark on light that has been traveling for nearly 14 billion years. The cosmic microwave background has become cosmology's Rosetta Stone, a map that we can read to decode the universe's history. From its overall temperature, we determine the expansion rate and age of the universe. From its tiny fluctuations, we infer the density of matter and energy. From its polarization, the way the light waves oscillate, we can potentially detect even more subtle signals. The gravitational waves produced by inflation itself, ripples in space-time that would have left their own characteristic imprint on this ancient light. There is something profoundly calming about the fact that this information has been preserved, that the universe has kept a record of its birth for us to discover. The photons in the cosmic microwave background are messengers from the deep past, having traveled through the expansion and evolution of the cosmos, while maintaining their testimony about the conditions when they were released. By studying them, we are quite literally looking back in time, observing the universe as it appeared just a few 100,000 years after its beginning, young, simple, and still bearing the marks of its even earlier inflationary past. Yet the cosmic microwave background, for all its revelatory power, is not the final word. It shows us the universe at 380,000 years. But inflation occurred far earlier, perhaps at 1036 seconds. The fluctuations we see are indirect evidence, quantum seeds that grew over time into the pattern we observe. For more direct evidence of inflation, for a smoking gun that would point unambiguously to the exponential expansion itself, cosmologists have turned their attention to a more subtle signal: the gravitational waves that inflation should have produced, and the unique way they would have polarized the cosmic microwave background light. Imagine space-time itself as a fabric, flexible and dynamic, capable of stretching and compressing, rippling and waving. Einstein's general relativity predicts that accelerating masses can create waves in this fabric, gravitational waves that travel at the speed of light, carrying energy and information about their source. In 2015, the LIGO detectors made the first direct observation of gravitational waves from merging black holes, confirming this century-old prediction and opening a new window onto the universe. But there is another kind of gravitational wave, far more elusive and far more profound in its implications: primordial gravitational waves produced by inflation itself. During the exponential expansion of the inflationary epoch, quantum fluctuations occurred not just in matter fields, but in the gravitational field as well. Just as quantum jitter in the inflaton field was stretched to cosmic scales and became density perturbations, quantum fluctuations in the metric of space-time itself, ripples in the very fabric of space, were stretched and became gravitational waves. These primordial gravitational waves would be fundamentally different from those produced by astrophysical sources like merging black holes. They would have wavelengths spanning the entire observable universe, far too long to be detected by instruments like LIGO. They would be weak, carrying only a tiny fraction of the energy density compared to other components of the universe, but they would be everywhere, filling all of space, a relic from inflation that has been traveling through the cosmos for nearly 14 billion years. How, then, could we possibly detect such waves? The answer lies in a subtle effect they would have on the cosmic microwave background radiation. As light travels through a gravitational wave, the wave's stretching and squeezing of space-time imparts a particular pattern of polarization to the light. Polarization is the direction in which light waves oscillate, horizontal, vertical, or at some angle in between. Most light is unpolarized, oscillating in random directions, but light that has interacted with gravitational waves acquires a specific polarization pattern. There is something almost musical about the mathematics of polarization. Cosmologists divide the polarization of the cosmic microwave background into two types, called E modes and B modes, based on their geometric properties. E modes are produced by density fluctuations, the quantum seeds we've already discussed and were detected years ago. B modes are more subtle. They can be produced by gravitational lensing, the bending of light by intervening matter, but they can also be produced by primordial gravitational waves. If we could detect B mode polarization with the right characteristics, particularly at large angular scales, we would have direct evidence of gravitational waves from inflation. The search for these B modes has become one of the most exciting quests in modern cosmology. Multiple experiments, ground-based telescopes in Antarctica and Chile, balloon-borne instruments floating high above the atmosphere, and proposed space missions are scanning the sky with ever-increasing sensitivity, looking for this faint polarization signal. The challenge is immense. The signal is tiny, and foreground contamination from our own galaxy's dust and magnetic fields creates confusing patterns that must be carefully separated from the primordial signal. In 2014, a team using the BICEP 2 telescope in Antarctica announced that they had detected B-mode polarization consistent with primordial gravitational waves, sending a wave of excitement through the cosmology community. The implication, if true, would have been profound. Direct confirmation of inflation and a measurement of the energy scale at which it occurred. But further analysis, particularly using data from the Planck satellite to map galactic dust more precisely, revealed that the signal was likely dominated by foreground contamination. The search continues, with improved instruments and better understanding of foregrounds, but a definitive detection remains elusive. As we drift deeper into this mystery, we must appreciate what's at stake. The amplitude of primordial B modes is related to the energy scale of inflation, how energetic the exponential expansion was. If inflation occurred at very high energies, approaching the scale where quantum gravity becomes important, the gravitational waves would be strong and might already be detectable. If inflation occurred at lower energies, the signal would be weaker and might require future generations of instruments to find, or it might be so weak that it's forever buried under foreground contamination, undetectable even in principle. The absence of a detection so far tells us something. If primordial gravitational waves exist, they must be weaker than early estimates suggested. This constrains models of inflation, ruling out those that predict very strong gravitational waves and favoring models where inflation occurred at somewhat lower energies. In science, null results are still results. They narrow the space of possibilities, guiding us toward truth, even when they don't provide the dramatic confirmation we seek. Yet the search continues, driven by the profound importance of the question. A detection of primordial B modes would be transformative. It would confirm that inflation actually occurred, moving it from compelling hypothesis to established fact. It would tell us the energy scale of inflation, providing a window into physics at energies far beyond what any particle accelerator could reach. It would give us direct evidence that quantum fluctuations in gravity, quantum fluctuations in space-time itself, are real, not just theoretical constructs, but actual physical phenomena that have shaped the cosmos. There is something profoundly calming about this ongoing search, this patient gathering of data, this careful analysis and reanalysis. Science proceeds not by dramatic revelations alone, but by incremental progress, by gradually constraining possibilities, by learning from both successes and setbacks. Whether we detect primordial gravitational waves next year, or next decade, or in some future century, the search itself advances our understanding, refines our instruments, sharpens our theories, and keeps alive the human quest to understand our cosmic origins. Meanwhile, across the vast expanse of theoretical physics, inflation itself is not a single theory, but a family of models, each with different assumptions about the inflatant field, different predictions for observables, different implications for the universe's birth. And while inflation has become the leading paradigm for the early universe, it is not without alternatives, and is certainly not without mysteries. To truly understand where we stand, we must explore the landscape of inflationary models and confront honestly the questions that remain unanswered. The beauty of science lies not in certainty, but in the process of questioning, testing, and refining our understanding. While inflation has become the dominant paradigm for explaining the early universe, it is not a single, monolithic theory, but rather a framework containing many specific models, each with different details about how inflation occurred. And beyond inflation, alternative theories continue to be explored, offering different explanations for the puzzles that inflation was designed to solve. Within the inflationary framework itself, models proliferate with remarkable diversity. There is slow roll inflation, where the inflatant field descends gradually down a gentle energy slope, rolling like a ball down a hill with very little friction. There is fast roll inflation, where the field tumbles more quickly, though still slowly enough to produce sufficient expansion. There is chaotic inflation, proposed by Andre Linde, where the inflaton starts at very high field values in a chaotic initial state and rolls downward from there. There is hybrid inflation, involving multiple fields that interact with each other, with one field maintaining inflation while another eventually causes it to end. Each model makes slightly different predictions about the detailed properties of density fluctuations and gravitational waves. Some predict a perfectly scale-invariant spectrum of fluctuations. Others predict small deviations. Some produce strong gravitational waves. Others produce waves too weak to detect. Some naturally explain why inflation lasted just the right amount of time. Others require more fine-tuning of parameters.